Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about neutrinos. So let's dive right into it. Well, first we have to understand this fact because this name is quite close to normal neutrons. We have to understand what the heck we are talking about. We are talking about an elementary particle. Now, this is very crucial to understand that in our world, our universe, there is layers. There are layers to things. Basically, you take a living thing, you do not go below cell. Why? Because if you go below cell, let's say you go into nucleus or mitochondria, you end up in a scenario where you are no longer dealing with living thing. Same happens with almost everything. If you are dealing with matter, you only go down to atom. You do not go below it, because once you go below it, you can fundamentally change let's say iron by removing its neutron or nucleus. Tampering with that, you can make it into something different. That's the whole reality of it. So everything in our world has a layer to it. So what we are talking about is one layer below atoms. Basically, you go inside an atom, inside a nucleus, inside a neutron or proton, you will find these things. So this is a very critical aspect. You have to understand we are dealing with extremely tiny things. Now, we are already talking about atoms, nucleus, neutron, proton, electrons, but somehow this puppy is still smaller than all of these things combined. So it's surprisingly, mind-bogglingly small. Now, another aspect you have to understand this is that atoms are mostly empty space because they have a nucleus which is very dense, it's almost unpenetrable, and then you have an electron shell around it. So you can easily go through if you are small enough. This puppy, very small. Now, another interesting aspect of it, it's everywhere. Neutrinos are everywhere. The moment I'm standing here, hundreds of neutrinos or sometimes even billions of neutrinos, if there is let's say a massive event like a nuclear high energy event has happened in anywhere in the universe, neutrinos will be coming out of it and they will be going through Earth like it's not even there. Matter is almost transparent to neutrinos. So this is a very interesting aspect, and they are created in high energy event. Now, thankfully, they do not require neutron star collisions to actually have an impact. It's not like a gravitational wave where it needs bonkers levels of energy. It can be done by human intervention with nuclear fission and fusion. So it is in human territory, so to say. Now, if you go even surface level onto this topic, you will realize standard model comes up. So what the heck is this standard model? Well, specified reality of it that you do not go below atom because you will reach a point where you are no longer dealing with matter. You are dealing with something different, or quantum world. So same goes here. Now we are dealing with elementary particle. What does that mean? That simply means till this point, scientists are very clever nowadays. Till this point, we have not found any way to break this particle anymore. Basically, that's it. In fact, back in the early days, atoms were the smallest unit. We physically did not have the technology to go inside it. Right now, we can go inside it, and the reality that we are finding, the quantum world, it's classified in elementary particles. Now, these particles, to best of our knowledge, to best of our understanding, cannot be subdivided. We cannot, like, no matter how powerful of a particle accelerator we can make, it will not go down any small. Now, we may discover newer particles, basically some particles that was hidden, but we will not find a way to, let's say, break an electron, because electron is a fundamental particle. However, let's say what happens if you collide a proton, you will get two up quarks and one dot quarks. What happens if you collide neutrons? You will get one up quarks, two down quarks. Now you're like, what the hell is this quark? That's the whole point. That's a fundamental building block in elementary particles. In quantum physics, these are the elements, things that you deal with. So in simplest way, simplify it to a basic level, it's like a periodic table for quantum physics. So we have a periodic table that we can understand, and it only deals with atom, because again, everything is arranged by atomic numbers, because once you go tamper with atomic numbers, you are changing the matter itself. So if you want to do that, you have to reach to this level. Like, this is normal layer, this is quantum physics layer. So this is why standard model will come time and time again. The moment you start to research in this puppy, this thing will happen inevitably. So it has multiple categories. It has quarks, it has leptons, it has glue, bosons, and bosons, Higgs boson. This puppy has it. So this is what we are dealing with here. Now, many high particles, many news articles will say faster than light, condition applied. Now, because of how our human brain works, we'll read the faster than light and we'll forget that there is a star mark applied. So reality is, this puppy is very small, and it's also very light. It's like ludicrously light. In terms of elementary particles, this puppy is like almost a lightweight. So not only it's smaller than atom, not only it's smaller than electron, it's very light also. What does that translate to? That translates to almost everything is transparent to this. That inherently, like, you can take X-ray or you can take gamma rays. That's the highest level normal photons that we have in this universe. You can stop it. You can stop it with few feet of let's say lead. We do that in our nuclear reactor, so we know how to do this. It's an actual tested reality. If you want to do the same with a neutrino source, where it's like, it's emitting neutrinos and you have to stop it, you're gonna need 1 light year of lead to stop neutrinos. Let that sink in. We can stop gamma rays in only few meters. We do that. Like, that's how our reactors are built. Like 10 meters, you good. 50 meters, like bonkers, but okay. At that point, it's like it can go bonkers and it still won't do anything. So we can stop gamma rays. Neutrinos, it simply does not. You need light years of material in order to stop it, because the interaction probability is ludicrously low. So this is one aspect of it, and it will only interact if it hits a neutron directly. That's why I specified. You have to remember the fact that atoms are mostly empty space, unless you are dealing with basically a neutron star. Matter is almost empty most of the time. So how the heck the fact that it travels faster than light applies? Well, here's the deal. Light has a c velocity in vacuum. Let's call it c. Now, nothing can exceed c, flat out nothing. However, light can slow down because it has the probability of interacting with things. It will slow down when it's traveling through a medium. So let's say, example, you shine a laser through water. It slows down, fundamentally slows down. It's like you can literally take the same distance. It will take longer for it to travel, and we call it refractive index, 1.3, 1.4, that sort of thing. So light has slowed down, but here's the deal. Nothing in physics is stopping anything else to travel faster than that. So think of this. A light would be 0.7 c, but something can travel at 0.9 c. That's what neutrinos do. Neutrino literally travels at almost light speed. Why? Because it's created in high energy event, so it has the oomph necessary to travel at speed. It's a very lightweight, so it does not require too much out of it. So it can actually maintain it, and because almost everything is transparent to it, it goes through without dumping its energy. Gamma rays dumps its energy. X-rays dumps its energy when it goes through things. This puppy, it does not dump its energy, so inherently it can maintain its light speed for almost every year. So neutrinos can move almost at c speed at any matter, any medium. So that's why it can travel faster than light in a medium. Keyword being there, faster than light in a medium. Light will slow down in a medium, but if you fire both of them in let's say a raw vacuum space, they will travel almost at the same speed. But again, neutrinos will be a bit slower. So if you fire them for, let's say, 10 trillion light years, for that distance, you will find photons will reach before that, and few seconds later neutrinos will reach. So how do we detect something that is this bonkers? Well, the reality is, it has to be done inside a medium. For telescopes, we generally want to remove things. Basically, we are like, hey, remove everything. Put a telescope in a vacuum. Put a telescope in actual space, or put it in interstellar space. So you get absolutely clean photos. Awesome. This is completely different. Interaction inside a medium is necessary. Why? Because if you have an interaction, let's say it interacts with some nucleus, it will cause what we call photonic boom, because it will travel faster than light inside that medium. So it will cause the photonic boom, or technical name being Cherenkov radiation. So when you see Dr. Manhattan in comic books, and there's like, why the heck that blue specific color? That color is signifying nuclear reactors. Nuclear reactors, I specified it, they do generate a lot of neutrinos. And again, if you're generating billions of them, some will interact. Again, not 100% of them, but some will. And those who will interact, they will cause a photonic boom. Basically, it's exceeding light speed inside a medium. So, things are happening. So that radiation has that blue glow. So if you have a medium that is big enough, like you have a medium where it's like a lot of probability event will happen, and you have a source that is powerful enough, you can detect it. If you have a nuclear reactor, you can detect it. That's the whole reality of it. So you need a bright source. What does that mean? That means you need something like a sun or a supernova, something of that caliber that generates a lot of it, so you can detect it. And there are 3 flavors of neutrinos. Now, neutrinos are fundamental particles, but they are not just one particle. Like electron is electron, photon is photon. This puppy does not follow like that. It's like electron neutrinos, muon neutrinos, tau neutrinos. It has multiple. And here's the interesting thing. One scientist put this quite eloquently. It's like, imagine you had a cat. Cat was walking. Cat somehow became a panther. Then panther walked, and panther became into something else. And then it went back to cat. Neutrinos does that in real life. We have tested it, we have observed it. It bonkers. Like, this thing is literal bonkers, even in quantum physics. That's saying a lot. So how do we deal with something this bonkers? Well, we need more tools. So our best reality at this point in time, if you simplify everything, how the heck we make a quote unquote telescope for this? Medium. That's the whole thing. This is one thing we understood very clearly. You cannot do this in a vacuum chamber. You need a medium. Now medium has to be as clean, as transparent as possible. Transparent to us, not to neutrino. Everything is transparent to neutrino, but to us. For example, if you're gonna take, let's say, argon, you're gonna be like, hey, let's get the purest argon, like absolutely clean, pure argon. You're gonna have a liquid state, so it's completely zero. So thermal vibrations are not causing interference with your system. Like you're gonna be like as clean as you can. Sometimes, let's say in Japanese scenario, they have a giant mine, and that mine has a huge chamber in that, and that chamber is filled with water. Now this water is the highest quality water ever made by man. This is like 100% pure water. Like at this point, they said like one of the workmen inside dropped a hammer that was a coated hammer. The coating survived, the hammer inside disappeared because the water was so reactive. Because if you make water absolutely pure, it has some weird properties. Basically, same reason we say do not drink absolute distilled water, it's bad for us. Same happened here. So you take a medium, whatever it is, be it ice in case of Antarctica ice, be it water in case of a dilute absolute pure, or some other scenarios where people are experimenting with other elements. You want it to be pure. You want the medium to be big. Basically, you are not dealing with 10-liter tank, you are dealing with gigaliter tanks. Basically 100 meter by 100 meter by 100 meter, or sometimes kilometer by kilometer. Yes, you heard that right, kilometer by kilometer. And there are people who are working on even bigger designs that will deal with 100 kilometer by 100 kilometer by 100 kilometer. Right now the second stage is focused on 10 kilometer cube, but you get the point. You want huge medium. Then because whenever that radiation is created, it's on optical spectrum, so you need photons multiplier. So why do you need that? Well, here's the, when you are dealing with a universal source, they are not producing gigatons of neutrinos, and most of them will not have, because it's not like a point source. When you are dealing with nuclear fusion, it's a human made thing. It's small, it's generating every neutrinos out there. But you are dealing with like like a black hole that is generating neutrinos in its accretion disk. That's like a very spread out. So you only gonna have one or two interactions at best case scenario when it's throwing billions of it. So you need very sensitive equipment to amplify that signal, whatever the signal is gonna happen. Like neutrino hit a nucleus of a water, and you want to see that actual signal, you need photo amplifier, because the photons that will be generated as a collision side effect would be very weak. So we need photo multipliers. Basically they are called it light bulb in reverse. So photons hit something, it excites electricity, and electricity gets amplified. So you have that. So one of the big one is Ice Cube Neutrino Observatory, which is in Antarctic. It has literally, they took that 1 kilometer, found the best ice there, no cracks, nothing, and they basically hot water drilled multiple sensors in that, and all the sensors, there is a giant grid. Benefit of that, if it can literally find out trajectory of a particle traveling, because again that radiation would be created in a pattern. That pattern can be detected by multiple point source, and utilizing mathematics, you can be like, okay, that literal neutrino came from that literal coordinate in space in time. There is a Japanese one which is Super Corona Japan, and that is also super huge. Well, another aspects are being built in America, and another one upgrade targeted for Antarctica, which will be even bigger. That will be that 10 kilometer cube. So bigger the medium, the better you have. The photo multiplier, we don't need too much in that department. We got that, but medium, that's the key. The bigger the medium, the better your chances, the higher the problem. Because right now the Antarctica one is like, hey, we detected 1 neutrinos in 6 months. So what we can expect in the future? What the hell is the point of studying something this bonkers? Well, reality is it's a direct window into high energy events, and we are talking about energy events in terms of equal time system, not neutron star colliding, not supernova explosions, and those can be observed using, well, other telescopes also, and gravitational wave also. This puppy specifically deals with things that are very high energy, but they are not creating gravitational waves, so you can only detect them using this puppy. So this allows another window, and science always requires multiple tools to work. You cannot be like, okay, this telescope done. No, you need hundreds of telescopes, hundreds of different kind of tools in order to calibrate your results. Like you will be like, okay, X-ray telescope, what the hell X-ray telescope say? Infrared telescope, what the heck they say? Neutrino telescope, what the hell that says? So you need a data collaboration in order to be absolutely sure about mathematics. For that reason, having a new tool that we humans are figuring out, that's awesome. That's like we are getting a new senses of eye, and this is not electromagnetic. You have to be mindful. Everything else at this point in time mostly deals with the electromagnetic spectrum. You are only dealing with basically photons and at different energy levels: radio waves, microwave, X-ray, gamma rays, infrared, ultraviolet, optical spectrum. All those are practically speaking photons, but we are dealing with here is something different, so it has a different signature to it. Yes, making a detector for it is ludicrously difficult, ludicrously complicated, but it does allow better understanding of like quantum world. It literally allows us to understand quantum world better, and there is a tiny probability, not a guaranteed one, tiny probability if we can solve this neutrino properly, we may figure out what the heck is dark matter. So it's not a non-trivial thing. And one annoying part is like when you're dealing with telescope, most of the time is like make the telescope bigger. So it's like, make a bigger Hubble telescope in space, awesome, that's what is James Webb telescope. So most of the time we just like make it bigger, make it in space. Same goes with a gravitational telescope. This puppy is the bit different. It's like we have to do this on Earth because we need medium, and we need large amount of medium. So it's not something that you can transport. You cannot build a rocket to ever that is big enough to transport 10 cubic kilometer of something like that. No, not happening. So its future is very grounded, so to say, but lot of potential is there in this field. Like, and this is a new field. To give you a context, it's a Japanese lab that that spent so much Japanese money. They got 2 Nobel Prize. So it is surprisingly active field. It's not like, oh well, in 1930s we figured this out. No, this is a new field. This is like, at the bleeding edge of science at this point in time. So this was my presentation on neutrinos. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.